Now let's talk about electrostatic potential. Electrostatic potential is pretty much just what it sounds like. It's what kind of potential do you have due to your electrostatic charges. Now let's go to the types of potential energy we know. We know there's gravitational potential energy. All right. You remember potential energy is mgh. And there's an elastic potential energy, where the energy stored in a spring is 1/2 kx squared. Now you see these don't have the same form. Just as gravitational potential energy is the gravity associated with a height due to some arbitrary reference, and the elastic potential energy is the energy with respect to this x. This is delta. It's really a delta x here. For electric potential energy, we're going to focus on the change of the energy. The change is what's important, not the absolute number. Now, what are the characteristics of electric potential energy? Well, first, it is quite literally the energy that a charged particle, so you have to have a positive or a negative charge, experiences when it changes position. So just like in gravitational potential energy and spring potential energy, position is essential. The conservation of energy laws tell us as potential energy increases, kinetic energy decreases, because the total energy must stay the same. So as you increase the potential energy, you actually slow your particle down. Similarly, as potential energy decreases, the kinetic energy must increase, or it speeds up. Now, this is energy, folks, so we're going to use joules. Now, if you have a uniform electric field, uniform means just that. It's not changing. So the electric field, we will show it like this: the same direction and magnitude at each point. So if you're here or here or here, the direction of the electric field is the same, and so is the magnitude. So if it's 2 newtons per coulomb here, it's 2 newtons per coulomb here, and 2 newtons per coulomb here. Now, a lot of times we talk about parallel plate capacitors. Parallel plate capacitors have, well, I lost my pin there, have a positive side and a negative side, and the plates have equal but opposite charges. So if this one is positive 3 coulombs, this one will be negative 3 coulombs. And we say that this parallel plate is charged to 3 coulombs. Now, if I move a charged particle in this field, let's look at what happens. I'm going to take my positive particle, I'm going to put it over here next to my positive plate. Positives repel each other, so the particle is going to want to come down here. It's going to speed up, and it's going to lose electric potential energy. Or if I take the same positive charge and I start down here, then it's going to take work to push it closer to the other positive charges. So even if it starts with an initial speed, it will gain electric potential energy and lose kinetic. Now, electrons can be a little tricky. Basically, what I recommend you do is figure out what would happen to a positive charge, and then the answer is just the opposite. Let's look at this. If I take this negative charge and put it close to another negative charge, it's going to repel. So even though the electric field is going down, the positive charge is going to want to go, or excuse me, the negative charge is going to go up. And it is actually going to decrease its potential and increase its speed. It's kinetic, which means increasing its speed. Similarly, if I have a positive and a negative here, they want to stay close. So I will have to pull it down. I'll have to do work to get it closer to the negative charges. If the particle is just moving this way, it's going to slow down. Now, we're going to go through a lot of formulas, so just be patient. What if we want to know what is the electric potential energy lost by a charged particle? And here's the key, folks, in a uniform electric field. So this is parallel plates. So I may say uniform electric field or parallel plates. Okay. The formula is quite straightforward. The change in potential energy. Remember, it's the change that's important. That we're going to measure in joules is equal to minus QED. The negative sign just tells you that we're going to lose potential energy. Q is the charge, and we always measure charges in coulombs. E is the electric field, and we always measure electric fields in newtons per coulomb. And D is the distance that the charged particle moves in the same direction as the electric field. So if the electric field is pointing this way, and the particle moves a distance d, then that d is positive. But if d moves against the charged particle, then d will be negative. So you need to be careful here. Clearly, the negatives will then cancel, and you wind up with an actual increase in potential energy. It's kind of tricky, but you can do this. Now, we talk a lot about voltage. And another term that we want to use is voltage, because the electric potential changes. So what if we looked at what the potential energy per unit charge was? Well, if I took the potential energy divided by charge, let me just call that the voltage. Another way to write this is change in electric potential energy is Q times the change in voltage. So delta PE is still the change in electric potential energy measured in joules. Delta V is a change in potential or the change in voltage. Please be careful. This notation gets students every year. It could be the change in potential or we just call it the voltage. It's measured in volts. And Q is, of course, a charge in coulombs. Now, voltage or potential is a scalar. It doesn't have a direction. So even though you have an electric field, which is a vector, the voltage is a scalar. So don't worry about the direction, but do keep track of sign, because you can have a positive voltage or a negative voltage, depending upon whether you have a positive charge or negative charge moving in your field. Now, what if we looked at the work done? Okay. If I have the voltage as a change in potential energy divided by Q, in order to move the particle, we have to overcome this potential energy, and so that's the work done. So another way to write this is the change in voltage is the work per unit charge. Now, think about this. 1 coulomb of charge, so 1 coulomb of charge will gain 1 joule of energy, or do 1 joule of work when it moves through 1 volt. All right. So what if this was 2? Delta V is work divided by Q. What if I had 1 coulomb of charge? So that's 1. We'll get how much energy or do how much work when it moves through, say, 2 volts. And clearly it's going to do 2 joules of work if it moves through 2 volts. Now, there are many sources for potential differences. I mean, we use these all the time. You stick the plugs in the wall outlets. This is a battery. This is a salt bridge with chemicals creating an anode and a cathode. And you all did this in junior high when you built a lemon battery. Same principles. Another formula, electric potential. Another way to relate electric potential is through the electric field and the distance it travels. So if I have an electric field, all right, in newtons per coulomb, and it's between, say, my two parallel plates. The potential difference between my negative side and my positive side, the voltage between these two parallel plates, is equal to whatever my electric field strength is, or here's my electric field strength, times the distance between the plates. So, you know what, that can be a little confusing. So we've taken on some pretty standard notation. Say I have a 20-volt battery. By convention, we say 0 volts is the negative plate. So whichever one is your negative, we're going to label this one at 0 volts. And the other plate is at whatever your positive potential is. Now, throughout here at any given point, you can see V equals ED. So the voltage increases. Okay, the electric field stays the same, but what changes is the distance you're moving. So if I were right here, the voltage would be the electric field times this distance. If I were right here, it would be the electric field times this distance.